Okay, hi everybody, it's Dr. B again, and let's go over some of the key things you should know for the Module 3 quiz. Pause the video as needed until you have each of these questions down. These represent the core topics for Module 3. What do the terms mole and stoichiometry mean briefly? Pause, check your answer, go through this multiple times. Once you got these all down, you have a pretty good understanding of the foundational material for Module 3. I would recommend rewatching the videos, redoing the reading, and having a look at the labs and the assignment before you go for the quiz. The term mole is just a number. That number is 6 times 10 to the 23. From that come things like molar mass and all that sort of stuff, but it's just a number. Stoichiometry is how we work with those numbers. It literally means element measuring. What's the molar mass of aluminum chloride? Pause, please. You'll just add up the individual average atomic masses and you should get the mass of the entire molecule. Aluminum, and you need a periodic table for that, checks in about 27 grams per mole. Chlorine is each 35.5. You have 3 of them. They total up to 133 roughly. What's the percent composition of ammonia? Well, to do that, we need to divide up the pie. If we have a pie of ammonia, and it's a mole's worth, I wouldn't eat it, but it would weigh 17 grams. That's because each nitrogen has a molar mass of 14 grams per mole, and each hydrogen has a mass of 1 grams per mole. There's 3 of them, so 17 grams per mole, from which 14 grams are due to nitrogen and 3 grams are due to hydrogen. Therefore, it is 14/17 nitrogen and 3/17 hydrogen. That is about 82 and 18% respectively. Draw the dot structure of hydrogen HNO, CO2, and CHCl3. Now, the textbook method for doing this, what you can certainly do, is to add up the total valence electrons, draw it out, and combine them. For many samples, there is a shortcut, which is to memorize the 4 most common elements: hydrogen, oxygen, nitrogen, and carbon. Honk if you love chemistry, and if you say them in that order, they form 1 bond, 2 bonds, 3 bonds, and 4 bonds respectively. Bonds come from single electrons, therefore hydrogen has 1 single electron. Nitrogen has 3 single electrons, but since it's group 5, it also has a lone pair of electrons. Oxygen has 6 valence electrons, which means it has 2 bonding electrons and 2 lone pairs. Carbon, group 4, simply has 4 bonding electrons. Makes it very easy to put things together. Don't forget those lone pairs. The halogens, generally speaking, form 1 bond each. Not always, but that's the way we'll do it in this course. And so put those together and you can rapidly come up with the dot structures for HNO, CO2, and CHCl3. Have a good look at this and convince yourself that the honk rules are obeyed. Hydrogen, single electron, you bet. This line represents 2 electrons. Nitrogen, 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pair. Note that you can make the bonds double or even triple. Okay, all the honk rules are obeyed. Carbon dioxide, does carbon have 4 bonds? You betcha. Does it have no lone pairs? That's correct. Does oxygen each one form the 2 bonds from HONC? It does. Did we throw in those 2 lone pairs? We did. CHCl3, notice also that you're always putting that most highly bonded element in the center. Oftentimes it's carbon. There's our carbon with its 4 bonds, no lone pairs, check. Hydrogen, 1 bond, no lone pairs, check. Each halogen, 3 bonds, 3 lone pairs, none. And the halogens have 3 lone pairs because they are group 7, sometimes called 17, which means they have 7 valence electrons. You're going to have to pair up 3 of them and have 1 bonding electron. You might be noticing that the bonding electrons share in order to form a covalent bond here. 2.4 grams of carbon reacts with hydrogen to form 3.2 grams of a hydrocarbon. So what's its empirical formula? Well, I don't know why they worded it that way. I mean, hiding within there is that it must be 0.8 grams of hydrogen, right? Now, if you just try to come up with gram ratios, that's not atomic ratios. Some atoms are heavier than others. You literally have to figure out how many atoms of each we are dealing with. And if 12 grams is a mole, and the mole is a number, that's how you can very quickly come up with a relative number of atoms. So we have 2.4 divided by 12. In other words, about a sixth, between a fifth and a sixth of a mole of carbon. And we have much more of hydrogen, more like 3 moles. So come up with those molar ratios, turn them into whole numbers by, and you'll see it when I click, dividing by the little guy, and you should end up with a whole number. So notice we have 2.4 grams of carbon, but if 12 grams is a mole, we have a fifth of a mole. If we have 0.8 grams of hydrogen, but each mole only weighs 1 gram, we have 8/10 of a mole of carbon. Maybe you can already see that this is a ratio of 1 to 4. When they get more complex, the trick is to divide by the smallest one. This will by definition make the small one 1, and the other ones will either become whole numbers or some very obvious fractions of a whole number, like 1.5, in which case, if that happens, you double everything, turn your halves into a whole, triple everything if you got a third there, etc., and you scale it up to whole numbers. This works out fine right here. This is methane CH4. At least that's its empirical formula. By the way, notice that since carbon forms 4 bonds and hydrogen forms 1, C2H8 is not possible. Try it and you'll see that this must be both its empirical and molecular formula. Calculate the mass percent of 5 grams of carbon that reacts with oxygen to form 10 grams of CO2. What they're saying, and this is popular in this course wording of this type, is that if you had 5 grams of carbon and turned it into CO2, you'd be using too much carbon. How much of it did you actually use? So CO2 is composed of 12, if you had for every 12 grams of carbon, you must have 32 grams of oxygen. Those are the average atomic masses. Look them up on the periodic table. So oxygen atoms are a little bit heavier than carbon atoms, and since there's 2 of them, it's a ratio of 12/44 and 32/44, right? And so that means that it's 27% carbon, basically. So if you have 10 grams, that means you only need 2.72 grams to make CO2. You have 5 grams. The amount that you used is 2.72 divided by 5 to turn it into a percent. That would be 55% of what was available. What's the molecular formula of ethylene? Empirical formula CH2 with a molar mass of 28 grams. I hope you're trying these on your own. Well, normally they have you figure them both out, but they give you the empirical formula. All we need to do is scale it up to the molar formula and adjust as necessary. CH2 only checks in at 14 grams per mole. The carbon is 12, each hydrogen is 1. Once again, we're looking up those average atomic masses. That seems to show up for so many of these problems. But we have a mass double that, not 14 grams per mole for 28 per grams per mole. To keep this ratio and come up with that molar mass, we simply double everything. 28 divided by 14 is 2. So the correct answer is C2H4. Give the formulas for sodium chloride, sodium oxide, calcium fluoride, and sodium phosphate. Recommendation: write one of each. NaCl, NaO, CaO, CaF, NaP. Write the charges above them. +1, -1. You should get those directly from your periodic table. Some of them you may have memorized by now. Na +1, oxide -2. Look them up. +2 -2, +2 -1, and +1 -3. Then 2 ways you could solve it. Just drop and switch, and you'll get the correct answers. If it's 2 to 2, you would lower it down to 1 to 1. So dropping this down to switch, it's still 1 and 1, therefore NaCl. Na2O, when we drop and switch, when we drop the +1 and the -2, the -2 switches over to Na, and you get Na2O. Similarly here, you'd get CaO, CaF2, and Na3P. Let's briefly explain why. For the example of Na3, PO4 I should have said. I said P, but it's PO4 for a phosphate. A phosphide would be P. Sodium is +1. Phosphates are -3. PO4 -3. It's a polyatomic ion. But ionic compounds are always uncharged overall. So if it was truly NaPO4, that's plus 1 minus 3, that would have a minus 2 charge. On the other hand, if we had 3 sodiums, that's now plus 3, totaling up, nicely offsetting the phosphate, which is minus 3, and that's why the drop and switch works well. Give the mass and number of moles of 1.204 times 10 to the 24 atoms of silver. I'll tell you a fast way and a slow way. You might recognize this number as being twice Avogadro's number. In other words, 6 times 10 to the 23 is a mole. That would mean you literally have that many, 1 mole's worth of atoms. But double that, you get 12 times 23. If we make that 12 10 times smaller and that 23 10 times bigger, we get proper scientific notation, 1.2 times 10 to the 24th. Number of moles, 2. Number of atoms, mass, and the number of moles. Oh, number of atoms is given. Number of moles is 2. And the mass, if you have 2 moles, well, each mole checks in, I think it's at 107.87 grams. So we simply double that to get 2 moles worth. And that's 215.7 grams of shiny silver. Dot structures, shape, and resonance provide the molecular geometry, shape, and bond angles of CO2, CH4, SO2, BF3, H2O, and NH3. This is a little more involved. The honk rules can take you a long ways towards saving some time, but they won't do all of them. I think I'll go ahead and explain the proper VSEPR, Vesper way of solving these. Let's apply it to CO2. Now, I don't have a drawing to show you, so in this case, I'm going to kind of walk you through it. Add up the valence electrons, and we get 4 for carbon, 6 for each oxygen. That's 6 doubled is 12, plus the 4 is 16. Draw the backbone, so a C, and I'm just miming it here, a COO, and let's connect them with a bond each. That accounts for 4 bonds, but we need 6, 12, 16. We need another 12, so we would draw the lone pairs around it, and then anytime you seem to have too many lone pairs, double them up, and you'll come up with a shape. It should be C double bonded to O on the left and the right. Don't forget those 2 lone pairs on each oxygen that went along for the ride. And if you have an AB2 system, one thing connected to 2 others and no lone pairs to occupy space, that'll simply be a linear structure. That's the best way they could spread out. You can't do better than 180-degree bond angles after all. Do note that the honk rules on this one can really save you some time. You know, I would very rapidly say the only way you could combine CO2 would be with 2 double bonds. Bada bing, you've memorized your lone pairs and you're done. Apply that to each of these, and I realize it's a little bit time consuming. And some of them are a little bit more challenging than others, like SO2. So in these answers here, I have little links. I really do like these Chem is Nate videos. The ones that use those really get right to the point. I chose some different authors for each one, but if you watch each one of them, they tend to drill through the same method that I said. Total up the valence electrons, draw the backbone, draw the lone pairs, double bond as needed, turn that into a shape. Shapes have implied bond angles, and you're done. I will admit that this problem requires a little bit more formal training than some of the other ones. So maybe this is one of the harder topics. You got a B in the course and you want an A, spend a little extra time on that one. How many reasonable resonance structures are there for the phosphate and the nitrate ions? Okay, it's worth pointing out what the scope of this course is. You will find it in writing for this course that it says resonance structures are beyond the scope of this course. However, they do point out that if you're looking at a couple like, say, the phosphate and the nitrate ions, they'll show how you can show that each of these structures is an average structure and that the bond angles are all the same, the bond distances are all the same, and, well, phosphate, you'll find, has 4 different resonance structures. The nitrate has 3. Since they don't want you to learn much more than that, I'm not going to explain much more than that. For common acids, I would simply memorize them. You'll see a slide where they're simply listed. I would memorize that, and let's practice them. HCl, hydrochloric. H2SO4, sulfuric. HNO3, nitric. HC2H3O2, Acetic. Notice they always start with hydrogen. H3PO4. Phosphoric. HI. Hydriotic. HF. I hope you're saying these. Hydrofluoric. HCl. Hydrochloric. Hey, let me point out some that aren't on the list. Give them or they maybe are on the list or aren't, but I'll say the formula, you tell me the name. HNO2. Nitrous. Very good. HF. Hydrofluoric. Very good. How about HClO4? Ha ha. Perchloric. Excellent. Were there any others? How about maybe, oh, there's really another. How about HBr? Hydrobromic. Very good. And here's a list of a bunch of them right there. It's good to memorize them. They're from here, you get there. There's a total list on a previous slide. Hey, those are some of the core topics for the Module 3 quiz. Good luck.